All right, the next test that we have is the comparison test, which is something that we've already done more or less when we were looking at improper integrals, the comparison test or the comparison theorem for improper integrals. This is exactly going to be, it's exactly the same idea. We have some series that we are given, and so that series would be a sub n. And then we want to go ahead and try to find another series whose terms are ordered in such a way. And by ordered, I mean there is some sort of inequality where our series that we start with, the given series, so let's just emphasize that the given series, our starting series, is the series of a sub n. So if our given series, if we can find another series whose terms are given by b sub n, and the b sub n is always strictly, or it's not strictly, but is greater than or equal to our given series term, and they're positive, or at least they're non-negative, because this is inclusive, so they're at least non-negative, then if you know the larger series terms converge, then the smaller series terms will converge. And then similarly, we can reverse the inequality if we can find series terms that are smaller than our series terms, and the series of the smaller terms diverges, then that forces the series of the larger terms to also diverge. Okay. So example 5, determine whether the following series converges or diverges. So the way I personally think about and how I do these problems is when we are given a series, look at it and then ask yourself, is it geometric? No. Is it telescoping? No. Is it a p-series? No. Geometric, telescoping, and p-series are series that we can figure out whether or not they converge fairly quickly. Geometric and p-series extremely quickly. Telescoping, it does take some work, but we can figure it out. Then there are series where maybe it looks like if we've swapped out all of the n's for x's, we might have a series that looks like something we could integrate. And then you could think about using the integral test. But that can be a lot of work because then there's limits involved and it can be a pain. So if you don't see anything like that, then you find yourself needing to use the comparison test. So what I would do here is I would look at this expression and I would think to myself, when n is exceptionally large, so when n is very, very, very large, what does this expression behave like? So really you want to use the idea of dominating terms. So for instance, so the idea is, what does this expression behave like when n is very large? Because remember, for series, if this isn't infinity, even if this is some exceptionally large number, like 10 to the 10 to the 10 to the 10, a very unfathomably large number, that series would still converge, no matter what this expression looks like, because it's a finite number of terms. That might be a very large number, but it's still not infinity. The sum ends, and because it actually has an end, it converges automatically. It's only when the series doesn't have an end, the sum goes on forever, do we have to wonder about convergence or divergence. So because any size number, it's as long as it's a finite sum, it would converge, we really only need to worry about what do the terms look like when n is exceptionally large. So we want to use the idea of dominating terms. So what we'll do here is, i.e., the limit as n goes to infinity of this expression. Now, we don't want to actually compute it all the way. We just want to use the idea of dominating terms to simplify the limit one stage. Or maybe two stages if you didn't do all the simplifying the first time. So the dominating term is n in the numerator. So n. This minus 1 won't matter when n is very large. That's what dominating terms means. And there's only one term in the bottom, and I'm going to combine this to get n to the 2 plus a half, so 2.5, so 5 halves. And then we can simplify this expression. So this would be 2.5, take away 1, that's 1.5, so this is 3 halves. So when n is very large, this expression behaves like 1 over n to the 3 halves. So I'll summarize that and say, when n is very large, n minus 1 over n squared square root of n is or behaves similarly to 1 over n to the 5 halves. So this right here is going to be the series term that we are going to compare our given series to. Okay? So what we have to do is think, is this larger than what we started with? So let's think about this. N minus 1, n squared square root of n. To get rid of this minus 1, we could add 1. And if I add 1 to the numerator, what happens to my fraction? It gets bigger. If I make my numerator bigger, I make my fraction bigger. So this inequality is true. And then from this stage here to this stage here was just a simplification. So this is just going to be equal. So what we have shown is that our original series term is less than or equal to this term here that we found. Oop. And I just noticed down here I wrote 5 halves. I should have written 3 halves. My apologies. Okay. And then we have to think, for the comparison, we need to make sure that we have a series term that is non-negative. So is this non-negative? Well, the smallest n is 1. So if I plug in 1, I get 0. And if I plug in 2, I definitely get something that's positive. So this is definitely what we have and what we need. So 0 is less than or equal to n minus 1 over n squared square root of n, which is less than or equal to 1 over n to the 3 halves. So there's our inequality. All of this that took place right here is great, but it's really our thought process. What we really need for the actual solution or mini proof to this problem is we need to establish the inequality. So that's important. And then we need to determine what the series with this term does and how does that relate to the smaller series term. Okay, so let's go over here and write down our little mini proof. Since we have this inequality, so since that's true, and the series from n equals 1 to infinity of 1 over n to the 3 halves converges, why does it converge? It converges since it is a p-series with p equal to 3 halves, which is strictly bigger than 1. So since that inequality and that series converges, so must the given series from n equals 1 to infinity, n minus 1 over n square root, is that n squared? N squared, excuse me, square root of n, by comparison. So that little bit right there is really the necessary part.